Welcome. In this video, we are going to do a brief overview of different types of spectroscopy. And we'll spend a little bit more time on some items than others. I'll also put out some resources for you if you're interested in digging into any of these in more detail. All right, so mass spectroscopy. This is one type of spectroscopy that we have already looked at. If you want to look back at our POGL that goes into mass spec in more details, that's on page 4. And basically what's happening in mass spec is the machine is ionizing our sample and sorting it by a mass to charge ratio and counting the number of particles it detects at each atomic mass. So the type of data we see from a mass spec, the y-axis gives us the intensity reading, which is going to be related to the percent abundance of each of these different masses of particles. The x-axis is the atomic mass, and the number of peaks will represent the different isotopes in your sample. So like in this example, we're looking at neon. It looks like there are 3 different versions of neon that each have different masses. So some have a mass of 20, some have a mass of 21, some have a mass of 22. We can tell from quickly glancing at this graph that the version of neon with a mass of 20 is the most abundant one in nature. And we can use information like this to calculate the average atomic mass as well. So that's the kind of information we're getting from the mass spec. It's mass versus the number of particles. Lots of our other types of spectroscopy involve the interaction between the electromagnetic radiation and your sample. And different types of electromagnetic radiation will interact differently with samples. So there's room on your notes to jot down some notes about the different types of radiation. So radio waves, microwaves, infrared, visible light, ultraviolet, these all fall in the same category of stuff that we call electromagnetic radiation. They can be low energy, high energy. They have different wavelengths and frequencies. And what we find is that different types of radiation will interact with matter differently and give us different sets of information. So that's what we are going to be looking at. For example, microwaves, when they bump into certain molecules, including water, they're going to cause the molecule to rotate around. And that's what happens when we're heating our food in the microwave. So different types of radiation react with matter differently. So with infrared spectroscopy, that's one type of radiation that we can use for spectroscopy. So we shine infrared radiation on a sample, and what we will see happening with infrared is that the bonds will vibrate. So if you looked at that PhET simulation, you could see this happening where the molecules kind of wiggle a little bit back and forth, so the bonds vibrate. And we can get some data from that. It looks a little bit like this. Infrared spectroscopy is not something that we go over in detail in AP Chemistry, so don't worry about interpreting these graphs. They get a little more complicated, but this is something you would look at in organic chemistry in college. But each molecule will give kind of a unique fingerprint, this graph here. So as far as what we should know is that infrared radiation is going to make the bonds move around within a molecule. That's kind of all we need to know about that. All right, spectrophotometry. This happens when we shine visible light on a sample. So again, notice the type of radiation we're shining on them is varying based on different types of spectroscopy. So this is when we're shining some light source on a sample. This is something you probably did already in regular chemistry. And what will happen is the sample will absorb some of the light, and then some of the light will pass through. And then you're going to have a detector over here that is going to detect, how much of the light went through and how much of it got absorbed. And there's 2 different outputs you might see. You might see absorbance or percent transmittance. It can report data either way. Typically, we see it in absorbance. That's usually how we have ours set. And we can graph this data, absorbance versus concentration. We should notice that the darker, more concentrated a solution, the more light's absorbed. So there's a direct relationship between the concentration of a solution and the amount of light that's absorbed. It's a linear relationship, should intersect the origin, and we will definitely, collect some data using this technique later on this year. And there's this relationship is sometimes referred to as Beer's law, and this can be found on your equation sheet. It looks like this. A equals ABC, and C is the concentration. So big takeaway is notice that the absorbance is directly proportional to the concentration. These values, the lowercase a and the lowercase b, are values that depend upon your experimental setup. So what wavelength of light you're using, what type of spectrophotometer you're using. B is the path length, so it's actually like the distance that the light has to travel. If we go back to this visual, like the distance the light is traveling through the sample. And often that value is 1 centimeter, but it can vary. So these things vary by experiment. And notice that this A times B is going to be proportional to the, or equal to the slope of this line right here. And again, we will definitely do some experiments involving spectrophotometry. So more on this later. Another type of spectra that we might see is the atomic emission spectra. And this is also something you may have already seen in regular chemistry. And we can apply an energy source like electric current. So we may have like hooked something up to electric current in class. And when we apply that energy, these electrons can become excited. And what that means is they will, it causes electron transitions, meaning the electrons will move between shells within the atom. So they can move between high and low energy positions within the atom, releasing or absorbing energy. And so there's actually two different types of data we might see. We might see what we call an absorption spectrum or an emission spectrum. And so we can observe the radiation that's either being absorbed or released from those electrons moving around. And so what kind of information we can get from this is we can get some information about basically the distance between those energy levels. So because what we're observing is the movement of those electrons between these different energy positions. So the energy we're observing in this, emission spectra tells us something about the difference in energy between those shells in the nucleus. Sorry, within the atom. So it tells us information about the energies of these various shells there. And then photoelectron spectroscopy, this is the one we've been talking about right now in class. And this is where we apply a higher energy source of radiation, like X-ray radiation, to your sample. And you're applying so much energy that we can actually eject the electrons from the atom itself. And we can measure what's being ejected from your sample. And the data collected is going to be your y-axis is your number of electrons. Your x-axis is your ionization energy. So basically how much energy was needed to remove those electrons. And it gives us information about the position of electrons within the atom and also the charge of the nucleus. So it definitely tells us some information about those electrons. Here is an example of how this graph is connected to the subatomic structure here. So we notice for lithium, we've got 2 electrons that are closer to the nucleus, so they take a little bit more energy to remove. You've got 1 electron that's in a further away position, so it takes less energy to remove. So we'll notice that the ones closer to the nucleus have a stronger Coulombic attraction to the nucleus. They're going to be harder to remove, so they have higher ionization energies. We can also compare different samples. Like in this example, I have an overlay of argon versus aluminum. And some things you will notice is that they both have, like let's look at aluminum, 1, 2, 3, 4, 5 peaks. Okay, so they both have that. And if we look at their electron configurations, aluminum's 1s2, actually I'm just going to start labeling it on the graph. So aluminum is 1s2, 2s2, 2p6, 3s2, 3p1. Okay, so there's 5 subshells, there's 5 peaks. Argon also has 5 subshells and 5 peaks. 1s2, 2s2, 2p6, 3s2, 3p6. A couple of differences that you want to notice that argon's 3p peak is a lot taller because it's got 6 electrons in the 3p as opposed to 1. And also notice that they're all shifted to the left. So argon's peaks are all to the left of aluminum's. And that's because aluminum, if you look at its nucleus, it has 13 protons, whereas argon has 18 protons in its nucleus. So argon's nucleus is more attractive. So it is going to be harder to remove electrons from argon than aluminum. So you'll notice all of its peaks are going to be kind of further to the left. So that's another way in which we can use this photoelectron spectra data, is to compare different atoms. All right, and that's the last of your spectra on your note sheet. I also want to point out NMR spectroscopy. It's not on our list of things that we're studying in here, but it's something that is, super important in modern chemistry, and so I will include some resources in that if you're interested in learning about that. That's nuclear magnetic resonance, and that's kind of cool because it has to do with, electron spin and stuff. So, all right, thanks for listening. Hope that helped. Let me know if you have questions.